Hey, Kathleen. Okay, so today we're going to be going over problem 11.6 from the book. So basic, actually, hold on a second. There we go. We're going to be going over problem 11.6. So you can see it's a disc that rolls, and we're also modeling how the disc tips over. So we have the sharp-edged uniform circular disc with some model parameters there. And you can see we've got this system of equations that describes the motion of the disc. So real quickly in part A, we're going to go ahead and classify this system. So first, is this system coupled or uncoupled?
Coupled.
It is coupled. That's correct. Is it linear or nonlinear?
Nonlinear.
That is correct. It is nonlinear. Do you know why?
The sine L and cosine L.
Yep, that's exactly right. We got some cosine L, sine L. We've got some h squareds floating around in there. So those are all nonlinear terms. Is it homogeneous or inhomogeneous?
Homogeneous.
It is homogeneous. That's right. Is it constant coefficient or variable coefficient?
Variable.
It is actually going to be constant coefficient. And that's because we don't have any dependence on time in here. So I think you're probably looking at so that very first term, you have a cosine L times h dot.
Yeah.
And so you do have an L and you have a cosine L in front of your h dot, but both of those are dependent variables. You don't have an independent variable in there that changes with time or anything, or such as time. And so that, rather than being a variable coefficient term, that's actually just a coupled term, is how we would describe that term, where you have like an L times an H or a H times H dot or something. Those are coupled terms. Those aren't variable coefficients. So this is just going to be a constant coefficient system. Does that make sense?
Yeah.
Okay. Is it first or second order?
Second.
That's right. And is it algebraic or differential?
Differential.
That's right. Okay. Any questions about any of these classifications? Okay. So, let's see. So part B, can you find an analytical or closed form solution for h of t, L of t, and omega of t?
If we linearize it, maybe.
Right, exactly. So just the system as it is, they emphasize U. They've got it in red lettering, bold, and italicized. So I'm not sure if that means there is a way to do it that you haven't learned about yet, that I haven't learned about yet. Short answer is no, we cannot find a closed form analytical solution for this. So that's exactly what we're going to do. I think that was Kathleen. We're going to go ahead and linearize it. And so what qualifiers from the previous list impede your progress? And so like you said, we have to linearize it. So it is nonlinear. And that makes finding solutions very difficult. Okay. So if we were given numerical values for MG and R, so our parameters, and initial values for our dependent variables, how would we solve this ODE? Or how could we?
Linearization.
So, how could we solve the previous ODE? So what it's asking for is how would we get some sort of approximation of the solution without having to linearize it. And the answer is going to be we'd have to do it rather than analytically, we'd have to solve it numerically. So we take our initial conditions, we figure out what our slopes are, and we integrate numerically, and we do that over small time intervals with some given initial conditions. And we can do that in something like MATLAB. So we would numerically integrate. We use MATLAB. The key here says MATLAB or Motion Genesis. Never heard of that except in this book. Apparently you can use it to numerically integrate things. Okay. So now we want to find conditions on omega nominal and omega dot nominal. So the nominal solution to the right satisfies the three nonlinear ODEs. And so if all of our H and H dots and our L's and L dots are 0, we have to find values of omega and omega dot that satisfy our equations. So that means this term is 0, that's 0. Let's, instead of that, let's go. So 0, 0, sine of 0, sine of 0 as well. So this first one is just 0 equals 0. Second one, we have a 0 equals 0. This one, we have 3 omega dot minus 0 minus 0 equals 0. So that means that omega dot nominal, what does it have to equal?
0.
That is correct. So omega dot nominal is 0, which implies that omega nominal is equal to some constant omega value. Questions so far?
Can you repeat the second part of part B about numerically integrating and all that?
Yeah, so if we're given values for mg and r, if we know what the mass is, we know what our gravity constant is, and we know what our radius is, and we have initial conditions for our states for H, L, and omega, and we actually probably need initial conditions for H dot, L dot, and omega dot as well. Then we could solve this by approximating with numerical integration. You can't do numerical integration with variables, like if mg and r are left as variables. And that's whereas if you have an analytical solution, then you could find the solution in terms of mg and r, but you can't do that with numerical integration. And so what we're doing is something like Euler's method, where we just start adding the slope times delta t to find the next, like our approximation of the value at the next time step, and then move on from there to find L of t or H of t. Does that clarify things?
Yeah.
Okay. Glad to hear it. All right. So Defined to the right are perturbations, omega x, omega y, and omega z, about their nominal solutions, which we have as some constant omega and 0 for omega dot. Using small approximations of section 18.1, linearize the equations of motion in perturbations about this nominal solution. So in other words, form ODEs that are linear in H tilde, L tilde, and omega tilde, and their time derivatives. So we're basically just going to try and linearize each term in our equations of motion here. So our first term, we had our H dot. So what is that first term going to go to if we linearize it?
Would it just be 6 times omega?
Yep, that's exactly right. So it's going to be 6. And so we're close to our omega nominal. So it's going to be 6 times capital omega. And so now capital omega is a constant value. If we couldn't do it by lowercase omega, because lowercase omega is a dependent variable, and then we have omega times H tilde dot, and that coupled term would be nonlinear. So good. All right, the L double dot term, do we need to linearize that one, or is that already linear?
It's already linear.
It's already linear, so it's just 5 L tilde double dot. So then we have this next term is 4G sine L over R. So what's our linear approximation of a sine term?
It would just be the angle inside of it.
That's right. So at small angles, sine of theta or sine of L is approximately equal to L. So we have the L there. So we're going to have a 4G over R times L tilde is the linearization of 4G sine L over R. And that's going to equal 0. This term is, when we linearize it, is going to go away. And that's because so we have an H dot squared. So parabola at our nominal point of 0, the slope is 0. So a linear approximation of H squared at the point 0 is 0. So that's why we don't have that term. Okay. Moving on to the next one. So we had 2 omega L dot. How are we going to linearize that one?
Two capital omega.
That's right. It's going to be 2 capital omega L tilde dot. And then the next term, cosine of L times H double dot.
1.
That's exactly right. The small angle approximation of our cosine is just 1. Okay.
I think I may be confusing myself and I may have missed something, but how are we able to transfer that into capital omega, which is a constant?
Yeah, so let's see here, see if there's something here. Small angle approximations, linearized equation motion. So basically what's going on, so omega, so we're going off of small perturbations from our state variables. And so in this case, our omega nominal is capital theta, is capital omega. One second. Excuse me. So yeah, I think just because we know that we're at small perturbations from our omega nominal, we're basically going to say that omega is approximately equal to omega nominal, which is capital omega. Does that make sense?
Yes. Thank you.
Okay. Okay, so part E here, we are going to solve the previous set of 3 linear algebraic equations for h tilde double dot, L tilde double dot, and omega tilde dot. So basically all we need to do is, instead of having 0 on one side of the equation, we want just L tilde double dot on one side of the equation, or just H tilde double dot. So if we have our, now let's go ahead and work it out over here. So we have 6 omega H, oops, H tilde dot plus 5 L tilde double dot minus 4G over R L tilde equals 0. So I'm going to go ahead and isolate L tilde double dot. So we have L tilde double dot equals, I'm going to add 4G over R times L tilde to both sides and subtract 6 omega H tilde dot from both sides. This is still a 5 L tilde double dot. So that means I have to divide by 5. So you have 4G over R divided by 5 comes out to 0.8 G over R. And so what's our coefficient in front of the H tilde dot if we divide the 6 omega by 5?
1.2 omega.
1.2 omega. Similar over here, we have 2 omega L tilde dot minus H tilde double dot equals 0. So what does H tilde double dot equal to?
Two omega, sorry.
That's right. It is 2 omega. Okay. Any other questions about linearization, or well, I guess part E was just algebraic manipulation. Questions about that? Okay. So moving on to part F. So we have the equation for H double dot can be integrated. So we have H double dot is 2 omega L dot to produce H dot equals 2 omega L plus C, where C is some constant. Substitution for H dot into there. So we plug this guy into there. Produces the ODE for L tilde, shown below. So to do that, determine omega, the stable omega, or the minimum value of capital omega, so that the lean angle L is neutrally stable for small perturbations. Okay. So essentially, what we need to do here So let's start here. So if L is nominally stable, what does that mean about its derivatives, L dot and L double dot?
They're 0.
They're going to be 0. So this term is going to be 0. Let's see. The minimum value of omega so that the lean angle L is neutrally stable. So what thoughts do you have about where to go from here?
I mean, I'm assuming the answer has L tilde and C in it, maybe? Because if we set the omegas to omega stable, then you kind of just combine them on one side and isolate it to solve for it. But I don't know.
Right. Yeah. Yeah, I'm trying to think through this right now. So the answer comes from, so I have the answer key here. And the answer comes from setting this term inside the parentheses equal to 0. And I'm trying to figure out why that might be. Any thoughts?
I mean, that's being multiplied by L tilde. But we know that L tilde is not 0. I don't know.
Yeah. Let's see, trying to think here. So we got this from this equation right here. And we plugged in H dot. Term value of theta, so that L is neutrally stable. Oh, might that be it? Okay. Think with me here. So, if something is stable, what does that mean about the poles of the system?
They're on the real imaginary axis, they're on the left side.
That's right. So, in this case, our poles are going to be, so our characteristic equation is we're going to have s squared plus 0.8 times 3 omega squared minus g over r. So we're going to take that and we're going to set it equal to 0. Right? So that's our, or not equal to 0, but our condition is we have to solve this for s. Let's actually do this. Let's keep going forward. So we're going to set that equal to 0. And so our poles are going to be negative b. So b is 0 plus or minus square root of 0 minus 4 times 1 times 0.8 times 3 omega squared minus g over r all over 2. So let's go. So what's 5 times or 4 times 0.8 gonna be?
3.2.
3.2. So we have 3.2 times 3 omega squared minus g over r over 2. Square root of that has to be, so this is going to be, so we have a negative here. So this is going to be a negative value. We're going to have two imaginary terms here, right? Is that necessarily true? Because we have a negative times if g over r is greater than 3 omega squared. That's okay. But so this term right here, our real part of this term has to be less than or equal to 0, right? So we're going to set this equal to 0, or it has to be less than 0. If it's equal to 0, it's neutrally stable, right? It's just oscillating forever. There's no damping. So it has to be less than 0. And so the way we do that, so we square both sides, and we're left with negative 3.2 times 3 omega squared minus g over r over 2. Less than 0 squared is 0. Multiply 2, divide the 3.2, and we have 3 omega squared minus g over r. So I divided by a negative 3.2, so that has to be greater than 0. And so then we have 3 omega squared is greater than g over r. Omega squared greater than g over 3r. And omega greater than the square root of g over r. Okay. And that's what we have here. Omega stable is greater than square root of g over 3r. Sorry, I just realized I was rushing through that a bit. Do we have any questions? Any confusions? If you don't have a specific question, but you do have confusion that you'd like to express, do so now.
So we looked at the equation they gave us after we took the integral, and we looked at the left side as if it was a characteristic equation.
Yes. So so what we did, so they gave us this equation. It's just, so we don't have any h in this equation. It's just L. It's just a differential equation, differential in L, linear in L, or L tilde. And so what it's asking for is okay, we need L to be stable. And we've learned previously that if the poles of the system are on the left half plane, the real part less than or equal to 0, then it's going to be stable. And so the poles come from the characteristic equation, which basically, if I were to take the Laplace transform of this, then, and with initial conditions equal to 0, L tilde double dot plus transform is just s squared L of s and then take the Laplace transform of the other term. You have plus 0.83 omega squared minus g over r L of s. You can factor out the L of s, and you're left with your characteristic equation. Is that clearer?
Yeah.
Okay. All right, let's see. Sarah, oh, did we lose Sarah?
Yeah.
I guess so. All right, moving on. You ready to move on?
Yeah.
Okay. Let's go to this last part here. Oh, what's going on? Okay, so part G. So when the disk rolls at the simple angular velocity, the magnitude of the velocity of the wheel's center is equal to omega r. Makes sense. So rolling without slip. Determine omega stable, and V stable is equal to omega stable times r. And comment on differences for a music CD of that and a bicycle wheel that. So we're just going to plug in our omega stable equal to square root of G, which is, so we're in centimeters, or so 9.81 over, so if R is 33.1 centimeters, that's 0.031 meters. So if I plug that in, I get 9.81, so square root 9.81 by 3 times 0.031. I get, so omega stable is greater than 10.3 radians per second, which when you multiply by r, it comes out to our velocity, our stable velocity is equal to 0.32 radians per meters per second. Omega stable for a bicycle wheel by the same process of omega stable greater than square root of G over 3R. Our bicycle wheel has a radius of 0.343 meters. That comes out to 3.1 radians per second. So and then V is 3.1 radians per second. Times are 0.34?
Yeah.
343. So that gives us 1.06 meters per second. So let's think about this a second. So the phenomenon that we're talking about is you roll a thin disk, and if you roll it fast enough, it'll stand up by itself, right? And it can even keep rolling sometimes, even if there's a little bit of tilt in it, it'll keep going. That's the L that we were talking about, that we're keeping stable. So what this is saying is that in order to roll a CD and have it stand up and keep rolling down the floor, it has to be going at 0.32 meters per second. But a bicycle wheel has to be going 3 times as fast, has to be going a meter per second. And that intuitively makes sense to me, that this bigger thing has to be going faster to remain stable. Any questions about that?
No.
Okay, perfect. Well, that is the end of our problem session.